Yep.
Should be, that's not me. That is,
Yeah, that's what you do. Yeah, you should do.
there's some echo for some reason.
You mute yours on there?
It's muted.
Or I mean,
This is muted.
No,
oh, no.
Hold on 1 sec.
it doesn't let you mute because it's trying to pull.
Yeah, I'll fix that in a sec. Hold on.
Is it any better? No.
Now?
Is it any better now? I
Yeah,
think,
that's it.
now good.
Okay. Welcome everyone to our very first talk in our IBM Discovery Institute seminar series. You will get a lot more invitations in that series hopefully soon. So we have a couple speakers lined up. This will continue, and we're also trying to make it more available on YouTube and these kind of things. In principle, there should be IBM participants. They may still be joining because they're at the remote site, and the idea is that we go back and forth between sites. So sometimes the speaker is here and IBM is remote, and sometimes the speaker is at IBM and we're remote. So we'll see how all this tech setup works out, but I think we have a good plan for today. And I will leave the introduction of our speaker today to Nick, because Nick is the one who invited him. So welcome, and I hope you guys enjoy.
All right, fantastic. So yeah, it's my pleasure to introduce Rafael Gomez-Bombarelli. So Rafa is the Jeffrey Chia Career Development Chair and Associate Professor of Material Science and Engineering at MIT. He did his undergraduate and graduate degrees at the University of Salamanca in Spain, and then postdoctoral work with Brendan Lovett, and then Alana Spuru-Guzik. And then he moved to industry actually and worked at the Culix North America company doing OLED, high throughput OLED discovery, and then came back to MIT as an assistant professor. He's won a number of awards. I'll just cite some ones here: the Sloan, the Dreyfus Machine Learning and Chemical Sciences Engineering Award, and the Google Faculty Award. If you've ever come across an autoencoder paper in chemistry or material science, this is the guy. 3,000 citations in 5 years or something crazy like that. So he's a big presence in the field. But with that said, I'm looking forward to your talk and welcome, Rafa.
Thank you, Nick. And, no one needs to do anything useful with the BAE yet, but hopefully soon. But in general, I think that's sort of an example of a broader theme of what I'm trying to sort of talk to you about today, which is sort of this continuum that we find between statistical methods and machine learning and physics-based simulations. And the reason why we're doing this, I think it's sort of transparent to everybody. The fact that IBM is working with you on materials innovation and sustainability is because it takes about 20 years for a material to make it to markets. And somebody has, it's like, oh, this sticky thing in a DuPont lab seems useful. Up until there is post-its out there, it takes about 20 years to get a material to market at scale. And if we're gunning for 2050 net zero, well, that means we have 6 years, right, to invent the materials that will be there in the 2050 net zero. So in general, right, we've got a materials, arbitrage and day ahead energy prediction, all those things will help with sustainability. But a lot of our problems and a lot of the things we need to sort out require just real world materials at scale, be it energy generation, energy storage, transportation, sustainable plastic, remediation of the damage we've done so far. So we've got these burning needs, and then we've got this amazing set of tools that over the last, 5 to 10 years have really changed the way we do some things, right? There's some tasks we used to think were really, really hard, and they turn out to be not that hard at all, and a computer can do them, right? And, we don't, from the Go game almost a decade ago, so sort of real-time strategy games like AlphaStar, Oriol Viñals, one of the big guys at AI at Google. He used to be a professional e-gamer before he went to machine learning. And then over the last sort of year and a half or 2 years, we've seen this sort of huge success in text and image generation, right? And all these things that we used to think that this took a lot of work, and it turns out it's a tractable problem. We don't know what explicit form it has, but it turns out even without knowing the explicit form of the problem, it may be solvable, right? And this has been through a combination of hardware that allows it, big data sets that can be used to train the models, and some work on algorithms, right? Like there's better and better algorithms, and all these things come together to do sort of things that we thought were really hard, including you know, the big scientific success story has been, of course, AlphaFold, right? But you know, the biggest ever success story is using ChatGPT to write cover letters. So this is like a high temperature superconductor cover letter. It's you know, I'm never writing a cover letter or reading a cover letter again, I guess. So what does that mean for materials, though, right? Like what's special about chemistry and material science? That is, you know, slightly unique. How do we co-opt those tools for material science? And the first question is that actually we're asking for a harder version of the task, because if we want to innovate and discover materials that are better than the best we have, that's beyond what typically machine learning models are trained, because models are trained to reproduce human performance, right? That you know, astronaut on a horse, it's a professional grade picture. It's not the best picture ever, but if we want to make a, you know, better, something that's better than steel or something that's better than polyethylene, well, that needs to be better than the best, right? So it's a different setup of the question. I postulate, you know, I believe, but this is not necessarily proven, that knowing the rules of the game, and in that particular case, this is the laws of physics, should help us, right? There's something called inductive bias, our own ability to, you know, have generalizable rules about how the world works, should help make machine learning easier. And we're never going to have as much data as they have in other domains, right? I will also say that it's not even clear what the data structure is in chemistry and materials, right? Text is clear, like we all agree how text looks like, and we all agree what images look like in the computer, right? It's pixels with 3 color channels. We all agree. How, you know, what's a material? It's like, well, if you're, you know, if you're in semiconductor, it's ultra pure silicon with a little bit of doping, right? But if you're a plastics person, it's a completely different. So it's not even clear what the data structure is. So a lot less how much data we have of each data structure. And the data part, I think, has been slowly changing, and I think people here will be aware of sort of this shifting paradigm, where in parallel to the more Edisonian pipeline, where humans have a working model of how the world works in their head, and design spaces that are sort of humanly tractable in their head, so maybe like 1,000 things one could possibly do, and do 1 or 2 experiments a day, process their feedback sort of through intuition and reasoning, and set up sort of this data lean discovery loop. Over the last sort of decade, the sciences have become accustomed to producing sort of larger data sets, right? And it feels more natural to work in these larger design spaces where there's like 1 million things I could try. And I set up some high throughput combinatorial tool that does 1,000 experiments a week. And then, of course, I don't digest that data just myself, but utilize data-driven models to drive decision. So the data scarcity part is being addressed, and I have some examples of collaborations where the thicker data pipes allowed for some of these principles to work. And I have sort of two ways, or there's sort of 2 fundamental ways we could sort of set these data-driven design stories for discovery. One is the forward problem, sort of screening. Like, well, if you know the list of possible solutions to a problem, and there is some method of scoring success, it's just a matter of moving through that space as swiftly as possible, right? And in our world, we use simulations. We don't have a lab. I collaborate with people that have labs. But for us, this typically means there is like a nice simulation I can do at scale that will score where a candidate is good. So I'll show you some examples where we sort of play this game where we understand what the design space is, what are the combinatorial rules for possible solutions, and we have a physics-based simulator that can hit the solution space, you know, hundreds to thousands of times. We can make surrogate models to expand that. Once we've modeled 1,000 entities, we can definitely do machine learning model that screens the rest of that space and have them sort of work together in purely digital world. And at some point, we need to hand it off for execution. And it can be to a person that needs to be convinced, or to a robot that needs to be constructed, right? And this is sort of the dichotomy of how to execute, whether things will be executed by a human being. And this is, in our case, all powered by this monster database where all our simulations live. So we have over 200 million DFT calculations, all of which have been executed and are stored through this Postgres database where everything lives. And in addition, and maybe going back to the BAE story from Nick, there is even one further step where, in addition to or complementarily to screening forward a design space whose rules we know, we can even be more aggressive and try to flip the function. And instead of going from potential design to predicted performance, we can try to set up an inverse function that goes from predicted performance to the designs that hits it, right? This is generative AI. And this is, the community has been doing this for 5 to 10 years. It's finally worked for text and images in a way that's amazing, right? And you prompt, this will be the prompt, astronaut on a horse on the surface of the moon. And the outcome will be the image. For us, this would be an OLED that is blue and high stability, and we'll probably get nothing because those two properties may be sort of scientifically incompatible, or maybe we get lots of answers. But we can propose this generative problem. I would say this has definitely worked for proteins. So there's startups out there that are taking protein designs to the clinic based on sort of these ideas. So my group is on this line, right? We utilize first principles as this sort of either training data or source of inductive bias. It extrapolates. We have a knob of how much we want to approximate. And that also automatically means how much we pay for simulations, right? So we typically are here in this part of the world, we're bounded between accuracy and cost through the approximations that we take. And here is the sort of this fast-moving part of the world where, without even knowing the rules of the game, one can be very, very effective. And if you think about it, the large language models use none of the rules of syntax that humanity has. If you ever took grammar in high school, right? None of that lives inside an LLM. So it turns out large language models worked without any inductive bias. It's true that the rules of syntax are sort of softer than energy conservation. So it probably makes sense to put in energy conservation in our AI for science. But in between, there's lots of things one can do, right? From injecting a little bit of data science into first principles to avoid wasting time on parts of the phase space you've already visited, right? And just write interpolators for the physics. And we don't do this, but folks have done this for climate modeling, right? And I don't know if you've seen this, but in climate modeling, instead of running forward the very expensive climate models, people train surrogate models on the outcome of these climate models that are 1,000 times cheaper. They get just as good climate predictions and much better uncertainty quantification because they can do lots and lots of simulations. Or injecting a little bit of symmetry, conservation invariances into machine learning models. And like I said, all of this is typically at the service of discovery and design. So I'll walk you through some examples. And the first one, which is a place where I think all the pieces sort of have landed relatively well, is in the design of zeolite catalysts. Zeolites are a class of materials that are used because they're crystalline and they have nanopores. So they are they're made of aluminosilicate. And there is about 200 known polymorphs, 200 known flavors of crystal structures that one can obtain with the controlled porosity. So they have these crystalline nanopores of 4, 5 to 10 Armstrong size. And their applications always have to do with the relationship of the pore and the task and something that fits inside. For instance, if you've ever seen, cat litter is made of natural zeolites. But for more sort of high-value applications, if you've ever seen an oxygen concentrator that people carry when they have breathing needs, those portable oxygen concentrators are zeolites that separate oxygen and nitrogen. Not perfectly, but they reach they push up the concentration of oxygen. They're using cracking for oil cracking. Small molecules will go into the pores, and because of the presence of aluminum sites and bronze acid sites, fluid catalytic cracking uses these materials to break up heavy fractions of oil into smaller fractions. And if you drive a diesel car, which is less common here than in Europe, maybe, there is zeolites for the NOx. So nitrogen diesel engines run hotter than gasoline engines, so they produce more nitrogen oxides. Cleaning nitrogen oxides out of exhaust uses zeolites too. So in addition to all these things you can do with them, there is hundreds of thousands of these materials, of these polymorphs, that have been predicted. And if you calculate their energy with DFT, they look just as good as the energies of the ones that you can mine out of the earth or make in a reactor. So for some reason, you know, we made 200, we seem to be missing 2.5 million. So this sort of a nicely combinatorial design space to go fish. And this nicely combinatorial, they're made hydrothermally, both in the lab and at scale. So these things are fortunately made in very similar ways in the lab and at scale in batch reactors, where you essentially put the inorganic precursors, control time, control concentration, and over the space of a week or two in what's essentially a pressure cooker, the precursors form into a gel, and out of the gel crystallizes a solid. And then there's a secret ingredient, which is the use of molecules such that the inorganic piece crystallizes around the pore and around the molecule. And the shape of the molecule induces the shape of the form that forms around it. Okay. It's also a world where when experiments fail, people typically report them. When you try to make a synthesis and you end up with either a dense phase, quartz or cristobalite, a dense isomorph, or you end up with just a glassy phase, people will report that. So the papers have lots of negative data, which is fantastic for machine learning. So in this case, we've you know, and we were in the first to think about fitting molecules inside zeolites with calculations, right? This sort of 30-year-old concept. Like I said, if the crystal grows around the molecule, ideally, one should be able to calculate how well a molecule fits a crystal and try to steer the crystal in formation in a certain direction based on the shape matching between the desired geometry and the molecule that one would put in there. And this kind of worked, but kind of didn't, because folks would typically design, you know, that molecule for this pore, and then they go make it, and a different pore gets formed that also fits this molecule, right? So folks were typically worried about binding, but they weren't worried about selectivity, right? It's not just that this molecule fits in this pore, but there's another 249 materials that could come out. We probably need to test how this molecule behaves against those materials too, and not just against the material that you want. So that's exactly what we set out to do, right? So this is a very high throughput example. There's no machine learning here so far. We just went big and screened all the known molecules. So there's about 1,000 molecules that have been used in zeolite synthesis in the literature. And there is a couple thousand more that we created with a BAE, with a generative model, just to fill up a little bit more space. And the 200 zeolites that folks have made, like I said, out of the millions that could be made. And we literally went and did the full matrix of how all these molecules fit into all these zeolites. And a bunch of them don't fit because the pores are smaller than the molecule. That's why this number is not the product of these two numbers, right? Because, and then we try different random configurations to make sure that we explore how these molecules fit. So we end up with this sort of very large matrix of not just affinity of, you know, this molecule hits well with this pore, but also selectivity. So not only it's good for this molecule and this zeolite are a good pair, but there is no better pair out there, right? There's nothing the molecule would rather do than fit this pore. And then we utilize data from the literature. Like I said, this is a community that reports negatives too. So in collaboration with Professor Elsa Oliveri, her picture's right there. Elsa was one of the first people to utilize natural language processing to read scientific literature. So in this particular example, they extracted about 3,000 synthesis recipes out of the literature from 70,000 zeolite papers. So the entity went and read, and like I said, this is a very standardized. Folks typically report what precursor, what temperature, for how long, right? The variables to track are easier than in other domains, and folks report negatives too. So they extracted a few thousand recipes. So we were able to match the recall between our calculation on the X, right? This is how our calculations would rank a molecule. And this is how the likelihood that it has appeared in the literature, right? For some of the zeolites, we really hit most of the literature result with just a few calculations, meaning that the calculation was highly predictive of what would be actually happening in the lab. And in addition, of course, there is all the temperature, all the other degrees of freedom, right? We only calculate the fitting. And then there is zeolites we do really, really badly for, which are the ones that show up when the molecule doesn't do anything. These are the zeolites that will form when the molecule doesn't really fit in the pore and it's just floating around. And of course, that's not correlated with anything, right? Because that's what you get when you fail. And then, like I said, this was in collaboration with human beings, right? We didn't interface this with a self-driving lab. We interface this with human beings, and those are very different modes of operation because when we're working with experimentalists, we need to show them the information in sort of digestible ways, and it needs to be made in a way that they can be compelled to make something and think that something is better than the state of the art, right? So there is a little bit of sort of user experience or user design. So we have a live web where all of this lives, and the web's still up, open to the world, where our collaborators could come in and navigate the key variables that we define that are correlated with experiment, as well as sort of their own intuition to explore. So in this particular example, right, these red molecules were big hits known from the 70s and the 80s in zeolite space, well patented, using industrial synthesis, not cheap. You can look at this molecule and if you remember your organic chemistry, this adamantane structure is not cheap to make. And then our colleagues were able to navigate the trade-offs between what they like and property performance to zero in a bunch of molecules that were, cheap, new, useful, that got made and characterized and made a few materials. And one of, I think, the coolest examples is that we were able to find molecules that were halfway good for two different zeolites. So in this example, right, this is the molecule from before. This is a total success to make this chabazite zeolite. This is the binding energy. So this would be like a really, really strong directing agent to direct towards chabazite. And this second molecule is a very good directing agent for AEI, a different zeolite. Right, this is why you have such a strong binding energy. So our colleagues were able to navigate the design space we had set to find these couple of molecules that are sort of on the diagonal, right? They're pretty good for chabazite and they're pretty good for AEI. And when you put this in a reactor, what you get is what's called an integral. So like a single crystal that is a random mixture of the two orientations of planes that differentiate AEI and chabazite. So we were able to make this control integral whose catalytic properties were as suspected, halfway between the more expensive AEI and the cheaper chabazite. This is for DINOX. I told you these materials are used for nitrogen oxide processing. And at low temperature, all the materials are just as good. At mid temperature, with some aging, they're still just as good. And then at really high temperature, at hydrothermal treatment of 800 degrees. So this is more what happens in trucks than what happens in the other way around. This is what happens in cars. They run very hot because the exhaust is very short. Trucks are more like this because there is more distance between the engine and the exhaust, so the gases have time to cool down. And in this example, you can see how the AEI, the more expensive material, is better. The integrals are sort of in between as expected, and the chabazite, which is cheaper, is the least performance. So it was a nice example where, this is screening, right? There's no machine learning here yet, but we were able to find a nice catalytic material. I think the sales of diesel cars are going down, so this is hard for this to make it to market. I mentioned the inorganic degrees of freedom. This is not work my group has led, but we're close collaborators with Olivetti and team who have utilized their own natural language processing recipes to train synthesis models. Just like we can predict how a molecule will fit the pore, then there is all of the other degrees of freedom. How long should I cook this for? Should I shake it? This is very important in zeolites. If you shake the reactor or not, because it's crystallizing, that's a big deal. That's a very important variable. So these folks have extracted all this data and have a couple of, especially this recent paper that just got accepted, using a machine learning model to predict, well, in addition to the molecule, you have this amount of aluminum and this amount of germanium, what is a zeolite that is going to emerge? So we have sort of a good knob on the organic and the inorganic degrees of freedom. And then in terms of machine learning, this is now we're in a position where we can go explore into the unknown. Because I mentioned, right, we've been exhaustive about a matrix that had 200 zeolites and 4,000 molecules. Now, there's a lot more molecules we could make, right? In this case, we've just repurposed molecules that we have already imagined, but the space of molecules we could find is actually much bigger. So we went out and enumerated this. It's about 2 million. So if you go, it's like all these molecules look similarly. They're all tetraalkyl ammonium salts, right? You need some positive charge to interact with the negative charge of the silicate. and they need to be stable because this is hydrothermal conditions at a couple of 150, 200 C for 2 weeks. So the design space boils down to tetralkyl ammonium molecules. So we took all the commercial halides and all the commercial amines and enumerated all the way we can put them together. And there's about 2 million structure directing agents that we could make. Now, the matrix is 2 million times 200. We're not going to do that with our simulator. That's now 400 million simulations. That's way beyond the budget. But we can definitely use a machine learning model trained on the data we have. So you can see the performance here. There is 2 pieces to the model, one that predicts whether something fits at all in the first place, so just a classifier of this molecule is too big or it's not too big. That's a very discrete decision. And then the second part of the model predicts, well, now that it fits, what's the affinity, right? What's the intensity of the interaction between the molecule and the pore? And now this model is just a neural network trained on descriptors. This takes milliseconds to call, so this is okay to call 800 million or a couple 100 million times and screen how all the possible hypothetical molecules could fit in all the possible zeolites that we're interested in. And then same game again, clean them up based on properties we can filter, put them in front of a human being, and I'm not gonna show the structures because we haven't published it yet, but there's been a couple more successes where we've been able to make new compositions of known zeolites. So we've been able to push the amount of aluminum up or down to limits that weren't possible before with the molecules that were known before. So we've had a little bit of experimental success in this one too. And happy to talk more, but that's still sort of coming. And as you see, these machine learning models that we train for property prediction, at the end of the day, what we're doing is structured property relationships, right? We have some molecule with some structure, and we want to predict its properties. So this goes back 40 years, right? This is not a new invention. The key at this point is how to input matter into a computer, right? And if you have a couple of 100 data points, the way this is typically done is through descriptors, right? So in the example I showed earlier, we have 4,000 molecules. We're more or less at the verge where we could do something more sophisticated. I have more examples of that. But typically, when you're in this domain, what utilizes is their own intuition and understanding of the problem to compress the nature of the problem to lower dimensional continuous descriptors. You know, if you're doing an electronic problem, it could be the HOMO, the LUMO, the polarizability, right? Or for our zeolites, it was the molecular volume, the sphericity, the larger axis, right? It's a very geometrical problem, so we utilize very geometrical descriptors. And this is, for instance, an example in collaboration with folks here at UIUC on polymer design, designing co-monomers for sustainable polymers. These folks at MIT have put forward a theme where they can include cleavable co-monomers inside plastics, such that they can bring a chemical stimulus, a reactant, that will react with these sort of cleavable co-monomers represented here by the little blue wall, and chemically cleave polymer strains and turn polymers that previously were not decomposable, such as thermosets, into cleavable and thus deconstructible thermosets that can be broken down back into small chemical entities that can be recycled. So again, these folks sort of designed this silyl ether additive, and it's kind of a very similar theme, right? Where there is a clear design space of what are all the silyl ethers I could possibly construct, right? I have an R prime, some double bond here to be included in the chain, such that the polymer that I make retains the properties of the pristine, non-cleavable, commercially used polymer. And in this particular example, again, we were in sort of couple 100-point territory, which is it's not trivial, but it's still it's not big data either. So we utilize descriptors. Is an example. You can see here the descriptors and the input variables. Of course, concentration of co-monomer, the concentration of cross-linking agent, another chemical that helps the polymer chains connect with one another, and then the chemical features of the chains or the groups that sit on the cleavable comonomer. And through some pretty aggressive regularization and uncertainty quantification, we were able to sort of achieve reasonable performance on the thermal properties, on the mechanical properties that we care about, class transition temperature and the bulk modulus, and then screen for new chemistries in a space that is in the tens of thousands, screen for new chemistries of R prime and rings here, in search for monomers that are as performant or more performant than the pure pristine polymer. So again, a very sort of forward screening story based. In this case, again, this one has no simulations, right? It was the labels that we had here were purely experimental. We did utilize some features that had some, partial charges that have some physicochemical origin. But at the end of the day, these are sort of very forward screening stories based on experimental data. If you're thinking about representation learning for when you have 4, 5, 10,000 data points, the architecture these days are called graph neural networks. I won't give you a long lecture on graph neural networks, but if you're in a place where you have 4,000, 5,000 data points, the natural choice these days for property prediction is not so much descriptors, but graph convolutions. It's always good to keep descriptors as a baseline, but typically these deep neural network architectures will do better than descriptors in the sort of 5,000-ish data point regime. I have my next example. It's also has a little bit more physics, a little bit more simulation, and it also has it wasn't executed through a human collaboration. It was executed through a robot collaboration, and the humans that made the robot. This is this is an example of what I was saying about graph neural networks. This is to predict the optical properties of a molecule, in particular the UVB spectrum, the color. And this is something that has been measured a lot. There is about 30,000 UVB spectra we could get out of the literature from databases. So there's about 30,000 molecule solvent combinations that we could find out there with peak UVB's peak that we could find. And it's a property that we can simulate reasonably well. It's not amazing, but sort of this workhorse simulation technique, time-dependent density functional theory, has sort of about 25, 30 nanometer error. And for folks that operate in other parts of science, that's about one color in the rainbow. So DFT is sort of about one color in the rainbow wrong. This is the correlation in our 20,000 points that we had at some point between what experiments say and what DFT says. So, it's okay. It's linear. It's not, it has some bias. The slope is not 1, but it's not trivial. So in this example, we did something that was sort of try to do the best of both worlds, right? So we have a theory that works, right? It's not amazing, but does some work. And we have a lot of experimental data set. So we took one of these graph neural networks, but we twisted it into what we call a multi-fidelity model to be able to exploit thousands and tens of thousands of simulations and thousands or tens of thousands of experimental data points. So what we did for this one is that we trained the machine learning model to predict first what theory would say. So there's a graph neural network that looks at the molecule and is trained to predict what theory would say. And then there is a second model that is trained to look at the molecule, look at the theory, and predict the experiment, right? So we sort of have two hopes. The first one is a proxy for theory, and the second is a proxy for how theory is wrong. And in this, I mean, we could do it, but I'm worried that I was about to say at the beginning, like, stop me, but then we can save it for later. When does this matter? Well, it depends, and this is, I think, a big take home for any data science machine learning tool over chemistry. The way to measure performance is critical. You probably all know machine learning models will memorize whatever you throw at them. So the training data, the stuff you show them, and you show them, they will memorize. So you cannot measure performance on the training data because you can assume that has been memorized. So then we need to test on a different held out data set. If our held out data set is completely random, there are chances that there could be huge crosstalk between the test data set and the training data set. And in this particular example, if a molecule is, the spectra of a molecule in water is in the training data set, then the spectra of that molecule in methanol is very easy to guess. You can just guess, it's kind of going to be the same as water because methanol is very polar. Boom. So this is what all the models do, and they all look amazing. Now, they're 5 nanometers wrong when we let the solvent molecules crosstalk, the solvent molecule pairs crosstalk between train and test. If we split by molecule, suddenly the models stratify a bit more, and all these tricks start paying off, right? Where if a molecule is in water in the training data set, then the methanol, ethanol, and all the other solvents are also in train. And then in chemistry, typically the most aggressive splits is what's called scaffold splits, where if all the IIDAIs are in train, then all the rhodamines are in test, right? We do this by chemical family, and then things stratify even more. And of course, the theory helps even more because there is more generalization in the theoretical simulations. That was our sort of key property prediction contribution in a much larger effort. This is the robot I was talking about. So this was led by Professor Klaus Jensen, who I think recently had a special issue on his 70-year-old birthday. This is a plate-based synthesis system utilizing a liquid handler and a plate-based physical characterization tool that can measure absorptivity, luminescence, and includes a solar generator to fry the molecules and measure stability. Robot arm to move the plates, a chemical reactor, temperature control reactor plate for controlling temperature. So this property prediction tool that I just showed you was sort of the representation learning innovation in a very large flow that goes from molecule generation with generative models, scoring based on the type of properties I just showed you, synthesis planning based on available retrosynthetic AI tools that can predict how to execute a synthesis based on the target molecule. Then this goes into a master controller that makes the tree of unit operations that the robot needs to carry out to make a molecule, execute in the robot with the plate reader and the various liquid handlers, characterize the key properties. Here is ours, lambda optical properties alongside solubility and photochemical or photostability, and an active learning loop that quantifies the uncertainty of these various machine learning models and selects new molecules to try to optimize the both performance. In this case, we wanted redshifted, stable, mid-solubility molecules in a self-driving loop. So of course, you can imagine how this involves many folks, not just our neural network and Professor Jensen, but also people that actually put the robot together. These were 4 new scaffolds that hadn't really been exploited for optical properties before. So this is the performance of the models at the beginning on the last round of molecules that will eventually be made. You can see that the models weren't sort of particularly good. There was no chemical space. And then this is where they ended after 3 rounds of self-driving space exploration. Some nicely read molecules here, covering all the solubility spectrum, and then slowly pushing the stability as high as we can. And in general, this thing ran 3 cycles of synthesis. It made a couple of 100 molecules. It had a little inner optimization loop to optimize synthesis conditions for low-yield molecules. So if a molecule was enough to be detected, but not enough to be characterized, it would go back and try higher temperature, different solvent, more time in an inner loop of synthesis to achieve enough material to characterize and fully close the loop. It's not just a preprint anymore. This got published the day before Christmas last year, so it disappeared from the radar. But I encourage you folks to check it out for the experimental piece, which I think was outstanding. I have another example with polymer electrolytes. I'll just show a picture of the robot. It's kind of the same name of the game, a self-driving robot with a AI-powered chemical space exploration. This one is not published yet, so maybe I'll just go a little bit fast and bring it to the sort of the more science versus engineering part of the talk, where I want to sort of highlight a couple of things we've done, bringing the fusion of machine learning a little bit more into the simulation world, right? Rather than just engineering how to screen through chemical spaces, trying to think about the interplay of physics-based simulators and machine learning models a little bit more intimately, or what I like to call differentiate everything everywhere all at once. So this is, you probably know, machine learning models are written in auto-differentiable languages. These are programming languages that expose analytical or tractable derivatives of any function that you can write, applying the chain rule. It's just the chain rule programmatically applied. And that opens lots of opportunities. So I'll try to highlight a couple. I think I'll run out of time before I show them all. One obvious one is in the spectrum of molecular dynamics and atomistic simulations. In general, right? When we do MD, we're trying to simulate, take a statistical mechanics approach to simulating matter. And at the end of the day, there's sort of typically three bottlenecks or three pain points in MD. The number of atoms to simulate, right? The more atoms, the longer the simulations take. The time scale, when we do molecular dynamics, we move the world 1 femtosecond or 2 at a time. So in order to observe microsecond or millisecond worth phenomena, we need to call our functions billions or trillions of times. So this is a big wall. And then we need to know the interaction energies between the particles, right? We're moving forward a Hamiltonian dynamics, and that includes the interaction between particles, which we can get from quantum mechanics, but this takes hours. And I just said we need to call the function, a billion or a trillion times. So a trillion hours of CPU time. That's a hard ask for the supercomputer guy. So where do we have AI sort of auto differentiation here? Well, it turns out we can take the quantum chemistry data, 200 million simulations I mentioned earlier, and just feed a function that says, well, given the quantum chemical energies, I will just train a graph neural network or some other function that from the atom positions predict their energies, right? Or rather than their energies from their atom positions, we can predict forces, which are the gradient of energies on a flip side. And this is our first derivative, right? This one we want to do analytically, or we want to do rigorously. For energy conservation, we want to rigorously learn forces that are the derivative of energies. Because we want to be able to train on quantum mechanical forces, not just quantum mechanical energies, because there is 3n forces. We have a lot more force data than energy data. So this is the first derivative. And if you write your energy function in a machine learning potential, then this first derivative you can get tractably in linear time. And then we just create a loss function that tries to have the machine learning forces agree with the quantum chemistry forces. This would be now our second derivative, where we can update our model parameters based on what on the derivative of the loss, right? How do we need to move the input parameters such that we minimize this loss? So this is our second derivative, right? We didn't invent this. This first one has been around from since Newton and Leibniz in the 1700s, and this one is stochastic gradient descent, which is the thing that powers training neural networks. And these two things come together, for instance, to train machine learning potentials that do things such as this example from last year, where we took a battery material, LGPS. If you've heard of this is a solid ionic conductor. It's used as an electrolyte in batteries, or proposed to be used as an electrolyte in batteries, because the lithium ions can move very quickly along the material. And unlike the liquids that we use for batteries today, this cannot catch fire. It's a solid, it won't leak out of the pouch. And even if it leaks out, this is not particularly flammable compared with the organic molecules that we use today. This material has been known for about a decade or more. And interestingly, it had been simulated by folks that had to pay full price quantum mechanics. And because they were paying full price quantum mechanics, they could only simulate for like 5-10 picoseconds, right? This was already a big price. And in 5 picoseconds, the only way you can measure the diffusivity of lithium in this material is by running the simulations very, very hot. So these folks in the red points here, they simulated the material at 800 Kelvin, which is way higher than you can actually measure it, but they were able to simulate it paying full quantum mechanics price. And they get this red trend. And then the experimentalists can measure diffusivity with NMR, and then they get the black squares. And the two things have more or less the same slope, but there's like a full order of magnitude difference between what the theories say this material should do and the experiments say it does. So we train on data that looks like this red one, and we fit the machine learning potential. Then we do regular molecular dynamics like everybody else, but we're not moving forward quantum mechanical forces. We're moving forward machine learning forces. And we managed to go much lower in temperature. And we find out that we agree with both. At high temperature, the simulations were right. And at low temperature, obviously, the experiments were right. But in between, there's a phase transition where the mobility, this thing is three-dimensional. There's a Z direction and a degenerate XY direction. And lithium can move along both. But the XY direction has a higher barrier. So that mechanism shuts down earlier at lower temperature. So what we see is this phase transition between fully mobile lithium at high temperature and lithium mobile only on the Z-axis at low temperature. And this difference is pretty much the entropy cost of freezing down the XY plane. So this was like a neat example of being able to just take quantum chemical data and scale it up to a much larger sort of realistic regime where we're able to finally observe sort of meaningful behavior. Let me see if I can just maybe fast forward to I have a couple more examples, but it's just same theme. We can take quantum chemistry, fit surrogate forces, and then use those forces to ask interesting questions. But maybe going back to my point about active learning, maybe it's worth spending a little bit more time here. How do we know that our model works in the regime where we want to use it? Well, this is a huge deal, and it's not solved, right? Essentially, what this means is that in order for me to do molecular dynamics or whatever in the class of problem you want to solve with machine learning, the model needs to be applicable in the regime that you really care about. But you only have training data in some regime that's probably not the one you care about the most. Otherwise, you would have already solved the problem, right? So there is this drift between the training distribution and the objective phase space you want to be at. And the only way we found, in text and in images, they've solved this problem by training on everything. And then all the data has been used, and there is essentially no data outside the phase space, right? If we knew that for simulations, we would be in a better place. But unfortunately, we don't have that ability to pre-train on everything. So what we need to set up is active learning. We need to somehow train the model on the data that is available to us, and then improve it in the places that are important but haven't been visited yet. And this boils down to the combination of uncertainty quantification, which is a big deal in machine learning, and it's an unsolved problem. And there is a long list of things one can try. I'll summarize by saying that ensembling is what works best for neural networks. It's not the cheapest. It's essentially you train a bunch of individual neural networks, maybe with different architectures, maybe with different data splits, maybe with different random seeds for all the initial conditions, and then utilize their disagreement as a measure of uncertainty. And then there's a number of other things, all of which are somewhat inferior, but cheaper. I mean, each member of the ensemble costs as much as the other, right? So at train time, you pay n times the price. At an inference, you pay n times the price. So suddenly when I said 1 billion calls, well, now it becomes 5 billion calls if we have a 5-member ensemble, right? And once we can quantify uncertainty, then there's the second half of how do I find the points that inform my model most? And then the way people had used to do this in sort of the 2010s was by running the simulation with the uncertain model. And the moment it found an uncertain frame, they would stop, send that frame to quantum chemistry, get the energies and the forces, retrain the model, and restart the simulation. This makes sense in a world where you're training very lightweight models, but with a neural network on 100,000 data points, you're not going to stop at 100,000 first point, run all the training again, continue the simulation. So maybe you do the full simulation, gather points, retrain, and set up this iterative loop where you pay full price simulation, get more points, pay the full price simulation again, and hopefully this converges to the phase space you care about. So this is our benchmark that we recently put out on uncertainty quantification. I would just say this is supposed to correlate model uncertainty against model error, and then they all look like fried eggs, right? This doesn't look like correlations, but this is ensembles, and like I said, this is the one that we trust the most. But like I said, it costs literally n times n being the number of members of the ensemble. So this is our third derivative of the day, which is the derivative with respect to uncertainty. Every function that we've written, we have access to its gradients. So we can literally say, instead of waiting for the system to visit uncertain points, we can drive the system towards uncertain points, right? So I can say, well, move the atoms in the simulation such that the next position is whatever the older position was, plus a move in the direction that maximizes the uncertainty of the frame while also maximizing its likelihood, right? So what is a step that seems likelihood, but also I'm really uncertain about, right? So this thing is differentiable. I just showed you, right? That the ensemble is just a variance. So it's a sum of difference of squares. So this is differentiable. And then this likelihood I can estimate based on all my training data, right? I have hundreds of thousands or tens of thousands of points I visited. I can quantify the likelihood of new points based on their energy and based on all the points I visited so far. So these two things are analytical and they're tractable, and I have their gradients. So I can literally start with my simulation, and instead of waiting for it to visit points that may be helpful, I can literally pursue these more uncertain points and explore phase space in a more efficient fashion. So this is something that has been the LGPS example that I showed you, for instance, among other reasons, worked because we did this and we were able to chase uncertain points and in a 5,000-6,000 DFT calls, get a trustworthy potential that we could take to new places. This is I'll just show you, this is just for kicks, but you can take another derivative, right? We take another derivative. This is the Hessian of the uncertainty. And in that image, we're seeing the normal modes of uncertainty. So we're moving the atoms in the direction that raises the collective uncertainty. And if you look at and pay a little bit of attention, it's like a Grothus chain where all the waters are giving each other their protons, which is a reasonable chemical phenomenon that happens in water. And it's also uncertain for our model, right? Because it's a lot of chemical reactions happening at the same time, which are all rare events that were probably not reflected in the training data. I'm going to skip through that one and get you my last example, because I also promised I would talk about this, so at least you've got the slide up. My last derivative of the day is the derivative along a simulation. That is, I can run a molecular dynamics simulation all the way to the end, and then utilizing the adjoint, that is the derivative of some loss function that I want to optimize with respect to every point in P and Q, in position and in momentum space. I can actually integrate the derivative of this loss function that I care about with respect to simulation parameters, initial conditions of the simulation, by what is essentially running the molecular dynamics trajectory backwards in time. So for instance, we can find the pair potential that makes a chain of beads fold into a helix, right? So we set up a loss that says at the end of the simulation, the structure needs to look like a helix and change the particle interaction potential based on how much the trajectory looks like a helix. Or we can fit to experiments. We can say, well, this is the radial distribution function of water. What is the interatomic potential whose forward propagation makes the RDF look like the water RDF, right? And this sort of gradient descent setup optimize, like I said, interaction parameters or even initial conditions. And with that, I'll just fast forward to the end to thank the team and thank you folks so much for your time. Yes.
Excellent. Thank you very much. We have time for a few questions.
Thank you for your great talk. Regarding differential simulation,
yeah,
we comment about scalability because you consider all possible gradient pathways, TGM simulation frame. They wonder about scalability of the method.
Yeah, I think it makes sense for things. I mean, it doesn't make sense in the context of unbiased simulations. But in the context of biased simulations, for instance, we've done examples. Typically, I think things that we can see in couple of thousand frames, so 2,000, 3,000 time steps, or thousands of time steps, we can backprop through. This linear cost in memory, if you do the adjoint, is linear cost in memory because the adjoint you calculate on the fly. If you were to save, like we do sometimes, you could also save all of these to disk And then you don't need to recalculate. You have the gradients forward, and you can calculate the gradients back if you save them. And then it's disk time, or you can just keep them all in memory at the same time, and then it's instantaneous, but it's a lot of memory cost. But in general, we've been able to propagate like a couple of thousand frames or time steps fine. So then this makes sense in the context of learning the bias that makes the simulation go somewhere. So when it's playing, I skipped through it, but thanks for the opportunity to bringing it back. So this is an example where we do this for pathfinding between a reactant and a product, where we learn the bias that makes the reaction go from the reactant to the product. So we have the product pull the reactant, right? We define our loss based on whether we've crossed or not, a little bit like transition path sampling. And at the beginning, the simulations are stuck in the one local minima, right? And they feel the pull from the other minima. And once they start diffusing through the barrier, we keep adding bias. So in general, it's scalable to things that can become diffusive in about 1,000 to a couple of thousand time steps, right? So if with bias, you can diffuse from one state to the other in a couple of thousand steps, then in principle, I think it's tractable. If it's something that is just like something like a large protein motion, where even if the bias is completely flat, like even if you have a completely flat surface, just the ballistic time to go from A to B is like 10,000 or 50,000 integration steps, then that's probably outside of what we can do. But I think in combination with bias, at the beginning it won't diffuse, right? It won't get over. But if in a flat potential you would see it in a couple of thousand frames, then I think that the framework should be able to reach there and come back. Yeah. Yeah.
Good question. In the context of LGPS solid electrolytes,
Yeah.
these are like silver line and darker, we get fast transport. Has there been any exploration on the diffusivity at the interface between the electrode and the electrolyte? These are typically hot regions in which you can get limited diffusivity because of like SAI formation of other interlayers.
Yeah, I mean, SCI is a chemical reaction. I mean, people are throwing so much compute and interest at SCI. We haven't really know. We've done this in the context of, we've done this for bulk diffusion. We're doing it for polymer. I show you, I skipped through my experiments on polymer electrolytes. We're also doing simulation of polymer electrolytes, which are a little bit messy, but interfaces, I think, are, the potentials, they can fit anything, right? Neural networks are universal approximators, so we can fit anything. The question is the tractability of, it's chemical reactions, so the timescales are large, it's rare events, right? Chemical reactions are rare events. So getting the SCI formation in a simulation, I mean, it's an aspiration, but it requires a lot of pieces that it's not low-hanging fruit. I think it's tractable, but it's not low-hanging fruit at all. So we haven't looked into diffusion or interfaces yet.
Other questions?
Yes.
In both the organic X story and the SQLite story, you have two neural networks, two models that were helping guide you to the target function. Can you just comment on when that's advantageous to use two complementary neural networks to make a single prediction versus trying to go with one?
Yes, that's a great point. So for we're running a benchmark. It's not, I mean, and all the numbers are sort of still in the air, but the take home is the more correlated the theories with the experiment, the more sense it makes to do this. If the data counts are very disparate, if you have 100,000 calculations and 100 experiments, you might as well train one model for the theory and just a little like tiny shallow regressor later, because these two things don't commute. And if they're poorly correlated, if the theory doesn't really have a good R-square with experiments, it doesn't help to pre-train and throw all this. So in general, we'll have some numbers coming out. The student is graduating in May, so the paper is going to come out before May. It's like so we'll have sort of some numbers of when things make sense based on the error between the low fidelity and the high fidelity model. But in general, in cases like this, like TDDFT to experiment, right, that was 20 nanometers. It makes a lot of sense. In other properties that we looked at, it may not make sense, or there's other things like multitask or transfer learning. Transfer learning means just train on the theory, then teach all the theoretical data and just refine the model for the other task. That may be more effective in other regimes. So we're sort of running a benchmark and we will have numbers for that.
Any other questions?
I recall a theory. I don't know
I like your
the statement.
model for predicting the theorem and to predict how it's wrong.
I will take the honor of the last question and ask a perhaps philosophical question, which is, yeah, you have all these wonderful collaborations with experimentalists, AI driving them. When somebody asks you, how much experimental data do you need to make these machineries work? What's your answer?
That's a good point. Oh, okay, this is perfect. I have my summary slide, but I blasted through it. So this is when it works. Like I would say, the common denominator when things have worked is that I would say it's an interplay between these two things. Actually, we should be able or these three things. Like if I trust my simulations all the way to in the zeolites, we had no experimental data of molecule fitting. We use the theory only for validation. So if we really trust the theory, we can be very aggressive and come in like, well, we trust the theory so much. Here are the predictions. Go make it. And we only need validation from you. There are other instances where we can warm start with in my polymer electrolyte. We extracted 5,000 data points from literature. We trained on that, and then we went into the okay. Well, we can start making things just based on what the literature people what was in the literature. And then what is the cycle throughput and frequency? So it really depends. I think it's very problem specific. But I would say you can see the active learning. The only example I have over chemistry was the hundreds of molecules that the robot made. So for molecules, it's probably in the hundreds, and making hundreds of molecules is brutal. But I would say it's an interplay of the trustworthiness of the simulator, how much we can start with historical knowledge, and both the thickness of the pipe and the speed of the flow in the line. I don't know if there's chemi people here and they're like blushing at my understanding of transport.
Yeah, I guess let me
Yeah.
twist it a slightly different way. Is how much of a warm start do you need to make this work? As in, like, what quantity of data do you have to actually extract from the literature?
Yeah, I think less than 100, there's no use for machine learning. A person should be doing it. And between 100 and 1,000, I think there's like a tension. A person could do it. More than 1,000, for sure, a computer is going to be better than a person.
Yes.
That's my, yeah. Huh? This is
Great. Okay.
Thank you,
Thank
Nick.
you for a wonderful talk. Yeah.
a pleasure.